Central limit theorem. In this lesson, we're going to be consolidating some of the ideas that we looked at in the investigation part of this, the sampling part 1. So the overview is the central limit theorem, often referred to just as CLT, is a key idea in statistics. It states that if we take many random samples of the same size from any population, the means of these samples will form a distribution that approximates a normal distribution. So we're saying that we're taking samples of the same size. The size of those samples is referred to as n. So what's the distribution of the sample means, or x bar? So we just said it would be normal. The parameters would be mu, and mu is the population mean. So if you take lots and lots of samples, let's say that the population mean is just here, you start to take the means of samples and you find that they're here and here and here and so on, and the mean of all of those should be the population mean. The variance, remember this parameter in a normal distribution is the variance. The variance is the population variance divided by n, which is the sample size we discussed. And that means that the standard deviation would be sigma over root n, often referred to as the standard error. And we've met that in the investigation, but now you've met it here if you didn't watch the investigation videos. This is true regardless of the shape of the original population distribution. We looked at this in the investigation. We started off with a discrete uniform distribution. It went from 1 to 10, and we took samples and we took means of those, and we found that it did start to approximate a normal. We also looked at a skew distribution with the binomial. We had a binomial that was 20 and 0.05, so very, very skewed, but that skewness gradually came out as we increased the size of n. And that's what it says here, provided the sample size is sufficiently large. Now, what we mean by that, sufficiently large, well, as we saw in the investigation, this takes longer to normalize than this one did, because this one had the feature of being symmetric, the same as the normal distribution at the beginning, whereas this one was very skewed. So you would take a larger n for this one than it would for this one, but as far as you're concerned, for tests and exams, there's usually a figure of n equals 30. So let's just go quickly through the key concepts here. So the key concepts are sample means. A sample mean is the average value of a subset of data taken from a larger population. So instead of measuring the height of everybody in the class, we just take a sample and we use that to approximate the population parameter. As sample size increases, the distribution of sample means becomes more normal. And that's the n thing that we were talking about just now. Standard error. The standard deviation of the sample means is called the standard error, and it is calculated as sigma over root n. We looked at that just now, where sigma is the population standard deviation and n is the sample size. Increasing the sample size reduces the standard error, and that should be clear to you because the n is in the denominator here. If you increase the denominator, you're dividing by a bigger number, meaning the sample means are more tightly clustered around the population mean. Importance. The CLT allows us to make inferences about population parameters, even when the population is not normally distributed. Strictly speaking, if the underlying distribution is normal, you're not using the central limit theorem, but that's not a distinction that you need to know about for this course.